Take it away.
Okay, thanks a lot, Thomas. So for everyone who may have joined late, so we just decided to slightly change the program for my lecture, meaning that we will talk today about the description of gravitational wave generation for a binary system in the weak field approximation. And we will try to talk about the energy fluxes and radiation reaction in a binary today, maybe a little bit tomorrow, so that we have time tomorrow to talk a little bit about numerical relativity and how to solve the strongly gravitating binary problem in general relativity. What I would like to start with, however, is actually to finish our discussion on gravitational wave detectors that we had yesterday. And I decided to swap some of the topics as well here. So the first thing that I would like to mention is actually the frequency ranges where our gravitational wave detectors are sensitive. So what do you think? We had this discussion briefly yesterday. So where do you think ground-based detectors such as LIGO are most sensitive? Where do they measure? Which frequency band, sorry, I should say.
My memory is around 100 hertz.
Mm-hmm. That's absolutely right. And let me actually write down a back of the envelope formula that lets you estimate what the frequency range is. So with that, let's go to my notes or my notebook. Share the entire screen. Yes. Okay, good. So today is the 24th of June. Oops. And this will be our section 3.3 on gravitational wave detectors continued. So just to give you a bit of an idea where interferometers are most sensitive, you can use kind of an approximate formula. So they're most sensitive if they have an effective arm length of roughly, and this is very, very approximate, really just order of magnitude, if it's roughly 1/4 of the gravitational wavelengths. So if we think about LIGO, or let me say ground-based detectors, because current designs are all rather similar, we are talking about, well, the actual tubes, the actual arms are 4 kilometers long, but we have these optical cavities where the laser light is reflected back and forth, so that we have an effective arm length of order of magnitude 100 kilometers. Now, if we want to take an estimate, let's take something like 750 kilometers, which is convenient to see that our gravitational wavelengths that we would be sensitive to is roughly at 3,000 kilometers. Now, if we translate that into a frequency, speed of light over our gravitational wavelengths, if we insert the numbers, we see precisely that we are most sensitive around 100 hertz. Of course, this is not just one peak, and I will draw the sensitivity curve in a moment, but this is essentially where LIGO is indeed, or the ground-based detectors that we have is indeed, they are indeed most sensitive. Now let's take another example. So we heard that briefly yesterday. LISA stands for Laser Interferometer Space Antenna. So that's a planned future detector in space, consisting of 3 arms, like in a triangle. And each of these arms has a length of about 2.5 million kilometers. So let's take that and make a similar estimate to find out where LISA will be most sensitive, in which range. So here the arm length is roughly 2.5 million kilometers. And that means we would be most sensitive to wavelengths of the order of 10 to the 7 kilometers. That is, if we now estimate the gravitational wave frequency, same formula, we would arrive at order 0.01 hertz, or at the order of millihertz. That is, our space-based detector, LISA, will be most sensitive in the millihertz regime. So, because we had yesterday the question of what frequency does our gravitational wave have, and that depends very much on the sources. So again, let me just get a little bit ahead of myself, and we will see all the development, all the formulas in the end of today or early tomorrow. So let's draw a sensitivity or set of curves where these detectors operate. And for that, let's take, oops, just get up here. So let's take here the characteristic strain. And I will just indicate the numbers very, very roughly. So this is all very schematic, but I think to give you an order of magnitude idea of what we're talking about, this will be sufficient. And then we have the frequency here. So let's start here with about 100 hertz. So this is where we have LIGO, and actually to be more precise, let me draw here about 10 hertz, here about a kilohertz, because that's actually the range where LIGO or our ground-based detectors are sensitive. Yeah, so this is well, LIGO, which has been advanced LIGO has been operating since 2015. We have Virgo, which is a gravitational wave detector close to Pisa, and in February last year, or in March, so just before the pandemic, Kagra, which is a gravitational wave detector in Japan, in the Kamiokande mines, joined the network. Okay, so this is what we have currently. So let me just roughly say since 2015. Now, I just said we have LISA. Let me put LISA here, and this is not to scale, so this is order millihertz. And this is where we will have our space-based detector, LISA, currently expected to fly around 2036. So this has been pushed a little bit to the future. And then in this even smaller range at nanohertz, we have this pulsar timing array that one of you mentioned yesterday, where we actually use beams from pulsars, so neutron stars, and the radio beams from highly rotating neutron stars to measure passing gravitational waves. So what we're doing is measuring very accurately the arrival time of these pulses to then infer information about passing gravitational waves. These are very long wavelengths, so the frequency is in the nanohertz regime. So this would be a pulsar timing array. Okay. Now, let me just give you one more piece of information. Again, we will see the formula for that, so the development of the formula for that towards the end of the lecture. But what one can find is that the gravitational wave frequency roughly scales as follows with the mass. We will learn about a new mass parameter, which I call curly m, which is called the Sherp mass. And this is related to our individual masses if we talk about a binary system in the following way, that we may have mass 1 to the power of 3, mass 2 of the power of 3, divided by the total mass, m1 plus m2, to the minus 1/8. So the reason why I'm writing that down, because now we can do a few estimates and think about the sources in the different frequency ranges. Now, if without filling in this formula, I invite you to do that at home. Let's think about sources for the individual detectors. So if you think about the ground-based detectors, what sources do we have here? which ones do merge in the hertz up to kilohertz regime.
Stellar mass black holes.
Stellar mass black holes.
Or sorry, stellar mass compact objects.
That's even more general, that's right. So, but let me write out stellar mass black holes because these are not the only ones that we have. And general compact objects, I suppose you mean black hole plus neutron star, again, meaning stellar mass, and of course also binary neutron stars. Okay. Other sources here. So the other ones that we already mentioned in the beginning of our lecture were the Coccolux supernovae. They also are expected to give gravitational wave signals in the high frequency range. So these are kind of the main sources here. Okay, so if we think about LISA, lower frequency, and since the frequency scales inversely with the mass, what do you think sources are for LISA? Which types of black holes or objects would merge in the LISA band?
Supermassive black holes.
Yeah, and well, actually we call them massive black holes. So
Massive
here we are
black holes.
talking about objects of say 10 to the 4 to roughly 10 to the 7 solar masses. What else?
Primordial gravitational waves?
Yeah, they hopefully, so that's one idea, and they would give a stochastic signal. So well, let me just generalize that stochastic gravitational waves. Okay, what else? Think about the stars that are orbiting Sagittarius A stars. So think about the stars that are orbiting around a supermassive black hole.
MREs, I guess, extreme mass ratio. Yeah.
Exactly. So these let me just call it MRE. So this stands for extreme mass ratio in spiral. We also have, let me just say that, so we also have our stellar mass black holes here, just when they are very far apart. So this is actually a very exciting possibility that we can observe these systems when they are very far apart in LISA and the millihertz regime. They will in spiral losing gravitational, so emitting gravitational waves, inspiring due to this energy emission, and merge in the LIGO band. So these we call stellar origin black holes. Let me just abbreviate that. This is actually really cool, where we go from LISA to LIGO and really have multi-band gravitational wave astronomy in the future, hopefully, with LISA and then the ground-based detectors at the time. Okay, and then if we think about pulsar timing arrays, nanohertz, here we are talking about what we call supermassive black holes. So with 10 to the 9, 10 to the 10 solar masses, and really also stochastic gravitational waves. Yeah, so this is kind of the landscape that we are looking at nowadays and in the future. So there's really, so just as you know, in astronomy with electromagnetic observations, I think in the future, we really expect to cover a large range of the gravitational wave spectrum with information about very, very different sources. Okay, so with all of that said, and I know I kind of went ahead of myself, so I had originally planned to talk about this tomorrow, but since we had this question yesterday, I thought it would be useful for you to have a bit of an overview where we're, what the gravitational wave spectrum is, what the landscape of sources is. So that was just to complete our discussion on gravitational wave detection. Okay, so.
Quick question, where are the mountains on neutron stars in frequency space?
So the binary neutron, so the binary neutron stars would lie in the order a few hundred hertz. So essentially what we would measure so, okay, let me start the other way around.
Sorry, I mean a single pulsar with
Okay,
non-spherical.
a single neutron
Yeah,
star.
where is
They would also lie in the few hundred to kilohertz range. So also within LIGO or possibly a future detector that is more sensitive at even higher frequencies. So at the moment we have a cutoff at about a kilohertz. So actually, even for the in-spiral, so for the multi-messenger event, for example, we only saw the in-spiral. We didn't actually see the merger because that was out of the frequency band. But you're absolutely right. So single neutron stars would lie in this range as well. Okay. Do we have any other questions before I continue?
I just want to ask, like, is there any other source that possibly, like, with the frequency higher than 1 kilohertz?
Sorry, can you please repeat?
I was just asking, is there any source that frequency is higher than 1 kilohertz?
Higher? Sorry, I didn't get the last word. I'm really sorry.
Higher than 1 kilohertz, I think.
Higher than 1
Yeah.
kilohertz.
So exactly. So there are ideas and plans for more sensitive ground-based detectors. So, for example, there are ideas here in Europe for what's called the Einstein telescope, which would have longer arm lengths and would be underground. So this would help both at low frequencies to damp seismic noise, and the hope would be to shift that a bit to higher frequencies. And then in the US, there are plans for NASA ground-based detector called Cosmic Explorer with an arm length of 40 kilometers. And there, the idea would really be to go to, or try to push to higher frequencies. Yeah. Okay, Jonathan is asking, oops, let me try to see, timescales. So he's asking about the timescales that are involved. Will it be possible for LISA and LIGO to detect the same black hole merger as they move closer together? So the timescales that we are talking about going from the LISA band to the LIGO band is about a few years. So if so the current mission time, planned mission time for LISA is about 4 years. So the hope would be that we would detect a massive stellar mass black hole binary in LISA, and that we would be able to forecast, to predict very accurately when it would merge in the ground-based detector band. So I'm not sure whether at that time, because we're now talking about the late 2030s, it's maybe not LIGO anymore, it may be something like Cosmic Explorer, but the hope would be that we could make very accurate predictions on when they would merge in the ground-based band. Okay, you're welcome. Do we have any other questions?
Yeah, I had a quick question. So do you know of any proposal of detecting anything that has to do with early universe cosmology other than primordial black holes?
Oh, so wait a second. So stochastic gravitational waves, yes. So they would originate, for example, from inflation. And there are predictions or ideas of how one could try to measure them or constrain them with LISA. So our cosmology working group is extremely active in trying to make these forecasts. Yeah, and then, oh, by the way, because you asked about primordial black holes, so they would be in the very low mass range. So they would also fall in the high frequency band, actually, if you're interested in those. Okay. Any other questions? No. So
just one more quick question. So how does the arm length of the interferometer grows if you want to probe more higher frequency, or does it go the other way?
It would so it helps. So as I just said, we have we can relate the effective arm lengths to the wavelengths, meaning to the inverse of the frequency. Yeah. But at the moment, I think we are more in the situation that we actually need to do some tricks to increase the effective arm length. So building something that's longer at the moment will still help us. Right.
Are there any more exotic gravitational wave sources that we haven't mentioned already?
Yes, yes, possibly. For example, people are studying so what generally we may call exotic compact objects. So something that's not necessarily in the standard model, but people are studying very actively boson stars. So compact objects that are made of complex scalar fields. And to see, whether the compact objects that we observe are really black holes or is it something else? And these boson so people are looking, for example, at axion stars. One example. So one of the, or two of the things that I am working on actively, which is also outside this kind of classical regime, is for one, studying the interaction between black holes and ultralight fields. So again, trying to use black holes to study axion-like particles. And we would probe the axion mass range between roughly 10 to the minus 20 electron volts to 10 to the minus 10 electron volts, depending on the mass of the black hole. So going from what's a candidate for fuzzy dark matter to the QCD axion. So it's actually really exciting. And then if you want to hear more about it, maybe we can have a discussion in the Q&A tomorrow. And then the other thing that I've been involved in actively is to test gravity, the strong field regime of gravity. So that goes towards the question, is general relativity really the theory of gravity? Or, do we have to modify it either to explain the accelerated expansion of the universe at large scales or to reconcile it with quantum physics? So usually candidates for quantum gravity predict extensions of GR. And then there can be new signatures, new features that I haven't listed here. But yeah, so gravitational waves give us a new way to probe the strong field regime. Okay, any more questions?
Yeah, I have a very nice question, which is, it seems like if you want to probe higher frequency and you still have interesting objects there, like for example, primordial black holes, then you should just build a smaller detector than LIGO. So it seems something easier to do than building LISA. So why is it not done? Is there a technical reason?
Yeah, so what I haven't written down here is what actually the strain is, right? So LIGO here, we are talking about this strain of 10 to the minus 21, 22. LISA, we are talking about 10 to the minus 17, 10 to the minus 18, roughly, give or take. If you go to higher frequencies, usually what happens is that you actually also need higher sensitivity, and that becomes technically very challenging. Yeah. No, and I completely agree that there are interesting sources to be found in the high frequency band. And in fact, for this ESA Voyage 2050, well, not mission solicitation, but really solicitation for future science projects. There were quite a few white papers for the very high frequency end, some for this Dezierz regime, so between LIGO and LISA, which is also currently not explored, and the low frequency end. And I think there's a really rich, very different sources that we can probe.
Sorry, follow up on that. The technical challenges are more about actual sensitivity of the detectors, or it's a problem of seismic noise and other types of noise?
Okay, so seismic noise is at low frequency, so that's why we have this cutoff here at about 10 hertz for the ground-based detectors. Then at the high frequency end, you get seismic noise and thermal noise. Sorry, not seismic, thermal noise and quantum noise, laser shot noise. There are quite a few sources that we need to get under control. Yeah.
Yep.
Okay. Any other questions? Okay, so if not, I will actually continue with a more regular part of the lecture and probably skip a few items. So which means that you would have to read the details in the classical textbooks, but I do want to at least talk about gravitational wave generation and the quadrupole formula. I'm not going to give you much of the derivation in the interest of time. and give an example for a binary with large separation, at least for today. So let's move up here to the next slide. So that was a next chapter, and as I said, I will abbreviate that a little bit. In the typed up lecture notes, I can still be more complete and give more information later on. So chapter 4, gravitational wave generation, and the quadrupole formula. And I think even if you have already seen that in the introductory GR course, I think you should see that one again, because this is really important. Yeah. So what we've done so far, or at least yesterday, was to look at the effect that gravitational waves have on matter. So we looked at the far field. So let's now look at the other end. Let's look at the source of the gravitational waves and how they are generated. So if we take our picture again, where we have here our source, here our observer, and some distance r between them. Let's now assume that we have a relatively compact source. Let's give that a size curly epsilon here, or var epsilon. So now we would be looking at a regime where the size of the source is much smaller than the gravitational wave. So that means we are in a regime, if we were to look at the binary, where the binary is still relatively far separated. Okay, good. Yeah, and in that regime, we also assume, again, slow motion and weak fields. Okay, good. So, so the usual assumptions, near region, slow motion, and weak fields. So we have our expansion that we talked about in the first two lectures again. And now let's assume Einstein's equations coupled to matter. And let's work in the harmonic gauge, but not in the transverse traceless gauge. Okay, so if you assume that, then we find that our equations of motion, our metric perturbations, satisfy the following equation. So wave operator, again, with respect to the flat space-time, h bar mu nu, and now we have the energy momentum tensor here on the right-hand side, and I believe I'm actually wrong with a factor here, so I think this should be 8, but let me check that afterwards. And if we were to include our natural constants, that would be the dependence here. Okay, so we would solve this equation using the Green's functions approach. Yeah, which is basically, which is pretty standard in theory for solving partial differential equations. I'm sure most of you are familiar with the approach from electromagnetism. Now, I'm not going to write this down in detail, but so one of the things that I do want to list is the following: that the general solution that we will find will actually depend on the past light cone. So if we talk about a solution, say at some point xi here, then it will contain information about the entire or the sum of the gravitational field in its past, within the past light cone here. Yeah, so the gravitational field is a sum of all the inferences. At a point, say TR, and I will write down what TR is a retarded time, what that is. And then let's just label the spatial part as X minus Y on the past light column. Yeah, so, and as I said, here TR is a retarded time, so that is T minus our difference in spatial vector divided by the speed of light. And the general solution that we will find if we go through the mass is the following. The gravitational potential h bar mu nu at some time t, some point xi, is given by 4 times the integral d3y 1 over the local distance, and then we have here the energy momentum tensity mu nu of the source at the retarded time and y. Okay, now to solve this, it's actually convenient to go to the Fourier domain. So again, only very sketchy. So we solve this in the Fourier domain. So if we do that calculation, then we would get that h bar tilde for the Fourier domain quantity of frequency and xi would be given by, again, the integral over d3y exponential e to the I omega, and again, the difference x minus y, the Fourier transform of our energy momentum tensor, omega yi, and divided by this difference. Now we make one more assumption, and that's the following. So we assume that the separation x minus y is much smaller than the size of the source. Yeah, so this x minus y is the distance between points within the source. We assume this to be much smaller than the size of the source. And in this approximation, we can actually write this e to the I. Okay, so we can, let me just write it slightly differently, which saves a bit of lines. So what this implies is that this difference between the points can approximate as being roughly just x, and then let's just call this r. So if we do that, we can rewrite our Fourier solution as follows. We would have h bar mu nu tilde of frequency, and now the radius equals to 4 e to the I omega r. We can take that out of the integral, divided by r. Now we integrate over the volume d3y and t mu nu tilde omega and y. Okay, so that was a very abbreviated derivation of that, and now we want to calculate this integral, this volume integral, in a bit more detail. Or we want to solve it, and we use the virial theorem together with our gauges to do so. And what is more, I probably should have said before, is that we actually use the gauges that we have to largely simplify this calculation, and instead of having to compute all of the components that we have here, we can actually compute only the spatial components and then reconstruct all the others from using our gauge. So we just outline that, and then I can sketch out the solution for our right-hand side here for our energy momentum contribution. Okay, so as I said, we use a harmonic gauge. Which was that the divergence of h bar mu nu equals to 0. Now in Fourier space, that becomes a relation between h bar 0 mu and 1 over, I over omega. And then we only have the spatial derivative here. So, and what that tells us is the following. So if you go through this carefully, we see that we only need to solve for hij in the Fourier domain. And we can reconstruct from this condition first the I0 components, and then finally the H00 components, so get everything else, which means that we can now focus on just solving this equation here. Okay, good. Let me just wait for a moment, and in case someone is actually taking notes here, before I continue on the next slide. Good. So let me continue. So one more ingredient that we need here is the Virial theorem that allows us to relate the spatial components of our energy momentum tensor to the energy density, that is to the T00 components of our energy momentum tensor. So, oops. Yeah. Oops. That is, we can relate the volume integral d3y of our energy momentum tensor spatial components, so t ij, omega, and y, not taking, so there are a lot of steps in between that involve repeated partial integration and evaluation of a surface integral. But in the end of the day, what you should find is that this can be related to minus the frequency over 2 integral d3y. And then here we have the 0,0 component of our energy momentum tensor. That is the energy density. And now, if you look at this very carefully, we can actually use this expression here and define that as a new tensor, which is the quadrupole momentum tensor. So, and this is actually important. So we define the quadrupole momentum tensor. And I labeled as ij. I'm also transforming back to time space. So energy momentum as a function of time is given precisely as this integral over d3y yi yj, and now the energy density, so T00 as a function of t and y. So this is pretty important. And this allows us to actually write the solution for the strain in the following form. So what we find now is that the strain hij bar of as a function of t and x is given by 2 divided by the distance. Let me reinsert our natural constants, Newton constant divided by c to the 4. And then here we have the second time derivative of our quadrupole momentum tensor as a function of TR. And I will use the notation here, oops, that dot is a time derivative, and I will also later on use the prime for radial derivative. Just for notation. And this is the equation that I said I do want you to see. So that is a quadrupole formula that relates the strain or the metric gravitational potential to the second time derivative of the quadrupole moment of our source. So this is pretty important. And so important, in fact, that I would like to use this and actually give you an explicit example for a binary system to compute first the quadrupole momentum tensor and then the metric perturbation. But let me stop here for a moment in case you have any questions.
There should be some indexes on I there, right?
Oh, yes, of course. You're absolutely right. There we go. Okay. Are there any other questions? Okay. So if not, let's go and look at an explicit example. Yeah. So that would be section 2.4. An example is a binary system in a circular orbit. Yeah, so that will simplify our calculation a lot. The more general case where you may have eccentric orbits, you can actually find very nicely in Poisson and Will. But here I would like to focus on circular orbits, and we will have a binary, say some mass here. Okay, and my drawing is of course not very good, so we should have the origin somewhat closer to the larger object because the origin coincides with our center of mass. So X and Y coordinates here. This is, let me label the larger mass M1, smaller mass M2. We want them to orbit around each other. They have some distance from the origin, R1 and R2. And as I said, so we have a binary. Let me label the total mass as capital M, and that's just M1 plus M2. I will also use the reduced mass, and that we call mu equals to M1 times M2 divided by the total mass. I will label the separation as L0. That is the sum between R1 and R2. And the positions given, or the radius is given by R, so R1 is given by M2 over total mass times L0. R2 is M1 divided by the total mass times L0, and that is because we are in the center of mass frame here. Okay, so what we want to do now is compute our gravitational potential and look at the strain and polarization matrix that we get out of here. Okay, to do this calculation, we are actually further assuming that we are really in the weak field regime where our two bodies orbit on Keplerian orbits. Yeah, so we're actually using formula that we should be familiar with from Newtonian gravity. So our orbital frequency, and as I said, we use Keplerian orbits. Is given by omega. Let me put a little k here for Keplerian. Is a square root of Newton's constant times total mass divided by separation to the third. And of course, the period, orbital period p would be just 2 pi over this frequency. Good. What we also need to write down are the positions in the xy plane. So we will use actually xy coordinates now. So let me just write this in for one example, and the others you will get by analogy. So the position x1, coordinate x1 for body 1 will be r1 cosine orbital frequency times t. And then you can write this out as m2 over m L squared cosine omega k times t. Similarly, y1 of t is r1 times sine of the orbital frequency times t. And then analogously, you get the coordinates for body 2. Good. So the next ingredient that we need for this calculation is our energy momentum tensor. So let me go to the next slide to write that down. Oops, here we go. So in general, as the energy momentum tensor for endpoint particles, this is what we are assuming here. And so we are completely neglecting any finite size effects. So we have just endpoint particles in the xy plane, and then that would be given by the sum of little n equals 1 to the number of our black holes, mass of the not black hole, particle, mass of each of the particles, and then here we have just some delta distributions, x minus xn, delta y minus yn, because we're in the xy plane, and then delta of z. Okay, if we insert that into our quadrupole momentum formula, we find the non-vanishing components for the quadrupole momentum tensor. And these would be given by Ixx equals to 1/2. And then this reduced mass that we introduced earlier, separation of the binary squared, 1 plus cosine of 2 orbital frequency times t. The yy component is 1/2 reduced mass separation squared 1 minus the cosine of 2 orbital frequency times t, and then the mixed component xy equals to 1/2 reduced mass separation squared, and then we have a sine 2 omega k t here. Okay, so now that we have our quadrupole momentum tensor, all we need to do is to insert that in our quadrupole formula that we have written down before. So if we do that, we find the following. So quadrupole formula. We find the form that Hij, and here I'm actually back in the transverse traceless gauge, can be written as minus H naught is strain times the polarization matrix. This is something that we've seen before, but let me write out what these different quantities is, and let me start with the polarization matrix. So here's a polarization matrix, Aij, can be written as cosine 2 omega k times t minus, so xx component, the yy component is minus cosine 2 omega k times t. And then we have a 0, and the off-diagonal components are just the sine of 2 capillary orbital frequency times t here as well. And then the rest are zeros. Now, if we look at this very carefully, we may see that we could actually also try to write this as, for example, here, the frequency of the gravitational wave times t. Or in other words, what this calculation tells us is that a binary with an orbital frequency, omega k, actually emits gravitational waves that are twice that frequency. Yeah, and this is a quite generic feature. So usually we can really directly relate the orbital frequency to our gravitational wave frequency by just a factor of 2. So yeah, binary with an orbital frequency omega k emits gravitational waves with a frequency, let's label that as omega GW, which is twice the orbital frequency. Okay, good. So that's the first part. And the second part is H naught or H0 turns out to be, or we can write this as 4 divided by the distance. Let me reintroduce here again the natural constants. So Newton's constant over c to the 4. Separation between the two objects squared, the reduced mass times this omega k here. Okay, so if we look at this, there are, if we think about how a gravitational wave signal looks like, which is for us a time series signal with a certain frequency and amplitude, we want to think about very carefully what can we actually measure and what is unknown or what can we try to infer. And in particular, what we can measure is the amplitude, let me just call that H naught, and we can measure the gravitational wave frequency that we, as I just said, can relate to the orbital frequency. What is unknown to us is the separation between the two objects. That's something that we cannot see directly. And we also do not know exactly what the reduced mass is. So to help us to rewrite the amplitude here, we actually do 2 things. So first of all, I will use a relation between the orbital frequency and separation that we've written down before, because we assume that we have Keplerian orbits. And then I also introduce a new quantity that I've briefly mentioned before. And this is called the chirp mass. The symbol we usually use is curly m here, and it's related to the individual masses as m1 to the 3, m2 to the 3 divided by the total mass, and then an overall factor of 1 over 5. So if we write down h naught or the amplitude in these quantities, and let's also use, the frequency f which is just 2 pi omega, we can write our amplitude as some prefactors here divided by speed of light to the 4th distance, and then we find here our chirp mass times Newton's constant over 5 to the 3, and then we have a factor of the gravitational wave frequency here over 2 to the 3rd. And the reason why, or what we can see from here, and actually what it turns out in the actual measurements, is that we can measure this chirp mass extremely accurately, or we can infer it extremely accurately if we have a long in-spiral signal. So this chirp mass really defines the frequency evolution, as we will see either later today, probably early tomorrow. So this chirp mass really defines the frequency evolution of our gravitational wave during the in-spiral. So that is something that we can measure much more accurately than the individual component masses. So, for example, trying to estimate M1 and M2 is much harder, much more difficult to estimate from our signal than this chirp mass. And that, for example, if you think about the multi-messenger events, these 2 neutron stars that merge and where we could see gamma ray burst, we have the chirp mass relatively accurately, and the individual component masses have huge error bars. So they are have estimates from, for one of the components between 0.8 solar masses to 1 point something solar masses. So they have large error bars, but the chirp mass we can get quite accurately. Okay, so, and that is here just, for our example. And the other important information is the relation between the orbital and gravitational wave frequency. Good. So I wanted to finish that part with actually an explicit example. So let's put in some numbers. And I decided to take as examples a Hulse-Taylor pulsar. So the Hulse-Taylor, does anyone know of here, or who knows what the Hulse-Taylor pulsar is and why it's so important?
Can I maybe ask a quick question?
Oh yeah, sure. Yeah.
So should in this last formula maybe be the G outside this this power of 5/3, or?
No, it's inside. So if you, basically go from the formula that I have here, insert the relation between the orbital frequency and the separation, which we just have a bit up here. Oops. Well, on the previous slide, which is the square root of GM and then divided by the separation to the 3rd. So if you insert all of that carefully, then you will get this power. Yeah, do we have any other questions? Okay, so if not, then let's just look at the Hulse-Taylor pulsar example. Oops. And the Hulse-Taylor pulsar is a system, the binary, is a system of 2 neutron stars, one of which is a pulsar. So Hulse and Taylor discovered that system in 1975, and could so found this as a binary system because there were apparent irregularities in the arrival time from the pulsar, and they monitored the system for quite a while. In fact, what we have seen, I will draw that picture in a moment, is that this system, these 2 pulsars have been, their orbital motion has been observed since 75. And that has been used to test some of the predictions from general relativity. And in particular, it has been used to see if you have things like radiation reaction. Remember, I mentioned, I think in the very first lecture, that there was a long debate of whether or not gravitational waves actually exist. Now, if gravitational waves exist, then they actually carry away energy from our binary system. As they carry away that energy, our binary will start, or the orbits of our binary will start shrinking. And that will, of course, reflect in the orbital period of our binary. Now, what people or astronomers have done is actually monitor the system since the 70s. And if you were now to plot here accumulated period shift versus time, and again, just very sketchy. So let's say here we start in 1975. Most plots that you will see, and now in the final lecture notes will add this plot, you would see the following. So assume there are no gravitational waves. The system would just move on the same orbit forever. There would be no period shift. However, if there is gravitational radiation, then, as I just said, orbits should shrink, the period should shrink, and one should see something like that. And this is exactly what has been observed. And the period shift within those roughly 30 years is about minus 40 seconds. And that observation basically concluded the discussion of whether gravitational waves exist or not, because these observations agree extremely well with the predictions from the quadrupole formula. And this is actually what I would want to do starting tomorrow, that we briefly look at the energy fluxes and radiation reaction, because I think that's important before we start talking about numerical relativity. Yeah, and the last example that I actually wanted to give for the Hertz-Taylor binary, what would be the gravitational wave amplitude if you could actually measure it? So for that, so let's calculate the amplitude. H naught, so the masses of these neutron stars. Okay, so let me also write this here. So this is a binary neutron star system. The individual masses are roughly 1.4 solar masses. So that's like a typical mass for a neutron star. Their separation, as inferred from the orbital period, is roughly 1.9 million kilometers. The orbital frequency, you can also infer from the period is about 3.6 times 10 to the minus 5 hertz. So the gravitational wave frequency that we would have would be something like 7.2 10 to the minus 5 hertz. Okay, and then the distance to us is about 6.4 kiloparsecs. So putting all of these numbers in, you would find that the amplitude of their gravitational waves is roughly 4.5 times 10 to the minus 23. So below what we currently can observe, but I thought I would give you this example, especially given the importance of the Hertz-Taylor binary pulsar for gravitational physics, and really as verification, a first observational verification for the existence of gravitational waves, even before light. Okay, so I will stop here. And as I said, tomorrow I would talk about the energy flux radiated in terms of gravitational waves, and give an estimate for the radiation reaction, all still in this weak coupling or a weak field regime, before we actually talk about how to model the strong field regime. Okay, so with that, I stop here and take any questions that you may have.
Helvi, questions?
I have a maybe you already addressed this, just a simple question. But you said that when you detect gravitational waves, you can detect H0 and then derive the chirp mass. I remember that when the gravitational wave signals were announced, they were actually giving the mass of the initial objects and the final mass of the merged object. And I wanted to know, how do you actually calculate those?
Okay. So there are two things, and okay, for that, let me just draw a plot that you would otherwise have seen tomorrow. So let's look at a typical gravitational wave evolution. So in the early stages, when our black holes or our compact objects are still very far apart, right? So the frequency is almost constant, will increase a little bit over time, and the amplitude will also increase over time. So this is the regime that we are describing. So here we are talking about weak fields, and usually we use post-Newtonian approximation, so going to a higher order beyond what we are doing today. And this allows us to get very accurately the chirp mass. So if you have a very long in-spiral signal, we can use the formula that we use today. Now, if you go, if these objects, because they emit gravitational waves, get closer and closer together, and they are close to merge, which is what we saw for the very first event, here the frequency and amplitude increase, everything is highly nonlinear. So in this case, we need numerical relativity. And here we actually, so for this last bit, we can actually much easier infer what the total masses of the system, because that's information that we get from these calculations in just very, very rough terms. So the very first detection was essentially a few orbits before merger. So here we really needed numerical relativity to identify the source masses. Whereas for example, the binary neutron star, we saw basically only the in-spiral signal. And that's why for the very first event, we got the total mass much more accurately. Whereas for this binary neutron star event, for example, we got the chirp mass much more accurately. Does that answer your question?
Yeah, that's great. Thank you. Just a clarification, when you say that everything becomes extremely nonlinear, you mean that the energy carried by the gravitational waves themselves backwards from the metric, or something different?
So here, the part that I label numerical relativity is the part where we can no longer apply any weak field expansion. So what we are doing is very basic, right? And you can think about, okay, what if I go beyond this slow motion expansion? What if I include higher order terms and say velocity over the speed of light? So this is what we call post-Newtonian expansion. But even that will eventually break down. And eventually we will have to solve Einstein's equations in full. And Einstein's equations are a system of nonlinear partial differential equations. So that's what I mean by highly nonlinear. And that's the regime where we have to actually use numerical relativity. Okay.
More questions?
I have a quick question. For LIGO detections, how much do we have to worry about the polarization of incoming gravitational waves?
So we are actually, so that's something we would try to calculate out. So, or in other words, we could get gravitational waves from all directions. So certainly there will be different polarizations. And so the reason, how can I put this? So at the moment we have more than one detector. So the initial LIGO planning was to have at least 2 detectors, precisely to get orientation and sources, as well as verifying a measurement. And now, of course, is having Virgo, hopefully Kagra in the future. So I just learned that they are actually not very sensitive yet. But with a whole network of gravitational wave detectors, I think we don't have to worry too much about polarizations, and this will actually help us localize where the wave comes from. right?
Thank you.
Mm-hmm. Yeah, but okay. So this is actually an external parameter that after we do the calculation, we can actually apply and then calculate out.
Peter?
Hi, can you say again how the post-Newtonian calculation differs from what we just did?
Mm-hmm. So think about what we are doing as like the zeros order, right? So for example, we still take a Keplerian orbit, whereas if you go, so think of it as a Newtonian order, and then think of a series expansion in characteristic velocity over the speed of light as an expansion parameter. Right. So this is in terms of how you would do the calculation, and then a different order in this post-Newtonian expansion, different effects become important. Right. So you would get, for example, radiation reaction properly only at 1.5 post-Newtonian order.
Okay, I was just wondering because we made several approximations here, but you're saying the most important one is the V over C, and that's the one that we try to improve upon. Like there were other approximations that were made, right? Like
yeah, but yeah, so this post-Newtonian calculation, the first one still take point particles and then have this expansion in V over C.
Okay.
Nowadays, we also know how to include finite size effects of the object. We also nowadays know how to include, well, spin effects appear at higher post-Newtonian order.
But still within the regime of linearized gravity.
Exactly. So this is still kind of in a linearized regime.
Okay, thanks.
Yeah. And maybe to follow up on that, because one of the things that we, of course, do in the end, because we need a full in-spiral or waveform, a signal, a template, a theoretical model that includes both the merger and the in-spiral. We actually have a combination of those techniques because numerical relativity is computationally very expensive. So we typically have order 10, 20 orbits before the merger. So what we do are actually two types of approaches. One is to say, okay, let's take our post-Newtonian model and extend it in a phenomenological way, and then try to match numerical relativity. And then there's another approach, well, so there's another approach which uses an effective one-body description of our binary, and again has then a parameterized way to extend through the merger, and then there are coefficients in that signal that is matched with or calibrated with numerical relativity. And having these models make a search much, much faster. So if you get a signal you want to identify that there is a signal and what the parameters are, then usually one uses these in-spiral merger ring down templates. Just to follow up on that. So in the end of the day, we take both techniques together to construct a waveform. And
how important is the deviation from a flat background spacetime, or is that not important? I mean, so if the event is happening far in the past, then maybe it would be important.
Yes, so the mass is, so that's another corrections that we do is actually take into account the redshift or the redshifted mass to then calculate back the source total mass. That's absolutely right. And that's actually a very good point because there are ideas and really attempts to use the measurement of gravitational waves to infer the Hubble constant. Because what we get from gravitational waves, the distance that I wrote down here is a luminosity distance. And then if you have a counterpart of, or if we know where the source comes from, we can learn about the redshift. And then we can start probing it for H0.
So the only effect of like an expansion of the universe is to just adjust by the redshift at the end of the calculation. You don't have to redo the whole formalism because the way you presented the formalism of linearized gravity, you did it with a flat background, but you're saying that's fine. Just adjust. So
usually so if you do the calculation, what you would find is essentially a factor 1 plus z difference.
Okay.
Between your source mass and the redshifted mass.
Okay, thanks.
Yeah, and again, I mean, I'm presenting the very basics, but yeah, we do have to go beyond the weak field regime. And numerical relativity, for example, doesn't make any assumptions about the background there. We really have curved space-time. That's why we need to solve it numerically. Does that clarify your question?
Yes, it does. Thanks.
Mm-hmm.
More questions for Helvi? Okay, if not, then we have plenty of time tomorrow for more questions. So let's thank Helvi again.